Now, question 1 is an if you know, you know type of question. Robert Boyle proposed that the volume of a given mass of gas varies inversely with the pressure when the temperature is kept constant. If we rearrange the ideal gas equation, we'll be able to represent Boyle's law with the equation P1V1 is equal to P2V2. And then they wanted you to state Charles's law. This law compares volume and temperature when pressure is held constant. So the volume of a given mass of gas is directly proportional to its absolute temperature, given that the pressure is held constant. Similarly, if we rearrange the ideal gas equation, we'll be able to represent Charles's law with the equation V1 over T1 is equal to V2 over T2. Though there are many assumptions made by this theory, the major and most well-known are: gas molecules are in constant motion. There are no forces of attraction between the gas molecules. Now please note the fact that I'm stressing no, since the question specifically asked you to make reference to ideal gases. Under no condition must you say little or weak forces of attraction between gas molecules. That's only true for real gases, and if this were a perfect world, we definitely wouldn't have that. The collision between the gas molecules are perfectly elastic, meaning both momentum and kinetic energy is conserved. Finally, the kinetic energy of the gas molecules is directly proportional to the temperature of the gas. The hotter the gas molecules, the harder and faster they shake, kinda like a teenage girl at her first rage out. Now let's get down to calculations. Pro tip: learning to substitute formulas into others to derive the formula that's actually helpful will do you a lot of good. Let me show you what I mean. This question asks you to calculate molar mass. Now you're probably thinking, what? Which formula? Kiss me. And kind of just, left that question. But hold on. Let's look at these two formulas and actually create something useful. PV is equal to nRT and N is equal to M over, a larger M. Tell me something though, what do these two formulas have in common? Since we're dealing with ideal gases, the previous question kinda hinted that we'll need to use the ideal gas equation. PV is equal to nRT. But right now, this is kinda useless because we need to calculate molar mass. But we know that the number of moles for any substance is calculated by dividing the mass given by the molar mass. This equation has two useful variables: the number of moles, which we can substitute into the ideal gas equation, and the molar mass, which is what we actually need to calculate. See where I'm going with this? So, in the ideal gas equation, where we have number of moles, we can insert M over larger M in its place. We'll only need to transpose and make molar mass the subject of the equation and solve for the given values. Yeah, no, it's not done this so. Because as CXC say, work. You're going to need to work a little bit harder for them crusty marks. Because CXC wants you to do some conversion. So first, let's work with the easier one. Convert 100 degrees Celsius to Kelvin simply by adding 273.15. This leaves you with 373.15 kelvins. Then convert 745 millimeters of mercury to atmospheres simply by dividing it by 760 millimeters of mercury. After, you should have 0.98 atmospheres. Finally, convert 247.13 milliliters to liters by dividing 1000 milliliters. And that's going to give you 0.2473 liters. Then now, you can substitute the values into the equation. After substituting, you're definitely going to get something around the area or ballpark of 53.60 grams per mole. And if you're working your units properly, you're going to get your units as gram per mole. So we good? When constructing the Born-Haber cycle for an ionic salt, the start is always the enthalpy of formation and the end is always the lattice energy of formation. After establishing the start and the end, you just need to fill in the path in between to connect both. This will complete the cycle. Now, the enthalpy of formation is defined as the energy released when 1 mole of a compound is formed from its constituent elements in their standard form under standard conditions of temperature and pressure. While the lattice energy is defined as the heat energy released to the environment when 1 mole of a substance is formed from its gaseous ions. The enthalpy changes used to complete the cycle must cause a change of solid lead to gaseous lead ions and of course the fluorine molecule to 2 gaseous fluoride ions. So the enthalpy changes you'll be needing are the enthalpy of atomization or sublimation of lead, the first ionization energy of lead, second ionization energy of lead, the enthalpy of atomization of fluorine, that's the fluorine molecule, and the first electron affinity of fluorine. Now, using the values given in the table, we can calculate the lattice energy. Also, since the table was given, if you were not sure of the enthalpy changes you were required to use to construct the Born-Haber cycle, the answers are right here, alright? It is important to note that up arrows represent endothermic reactions and thus must have positive values, while down arrows represent exothermic reactions or processes and must therefore have negative values. Also, when constructing the equation to complete the lattice energy, if you go against an arrow in the cycle, you must flip the sign of the enthalpy value, and if you go with the arrow, you must keep the sign the same. Negative lattice energy is equal to negative enthalpy of formation of lead fluoride plus the enthalpy of atomization of lead plus the first ionization energy of lead plus the second ionization energy of lead plus 2 times 2 multiplied by, please note, 2 multiplied by the enthalpy of atomization of that fluorine molecule, simply because you'll get 2 fluorine atoms, and 2 times the electron affinity of that fluorine. Okay, so simplify and you should get your lattice energy being equal to negative 2526.88 kilojoules per mole. As the ionic charge increases, the lattice energy increases. As the atomic radius increases, the lattice energy decreases. Based on the reaction described, the yellow precipitate formed is silver iodide. Therefore, the ionic equation must show the combination of the silver and iodide ions as follows. Ag plus in its aqueous state, of course, plus I minus also in its aqueous state will come together to form AgI in its solid state, which is our silver iodide. Yeah? Long story short, the precipitate dissolves in excess ammonia. This is because a soluble complex ion is formed when ammonia is added to silver iodide. Silver nitrate is often acidified with dilute nitric acid when testing for iodide ions to prevent interference of other ions such as hydroxide and carbonate ions. By acidifying the silver nitrate solution with dilute acid, the carbonate ions and hydroxide ions are neutralized and converted to carbon dioxide and water respectively. This ensures that the only reaction taking place is the formation of silver iodide precipitate with the silver ions, allowing for a more accurate and reliable test for the presence of those iodide ions. Hydrochloric acid is not used to acidify silver nitrate solution when testing for iodide ions because hydrochloric acid itself can react with silver ions to form the silver chloride precipitate. When chlorine water is added to a solution of potassium bromide, the chlorine water will oxidize the bromide ions to bromine. In turn, the chlorine will be reduced to chloride ions. A color change from colorless to brown should be observed. When aqueous silver nitrate is added, a white silver chloride precipitate is formed. The term dynamic equilibrium describes a chemical reaction in which the forward and backward reaction occurs at the same rate. When dinitrogen tetroxide, a colorless gas, is added to an evacuated chamber at room temperature, we would observe a colorless change to brown, nitrous oxide. This color will gradually get darker until the color change remains constant. Le Chatelier's principle states that a system at equilibrium will adjust to counteract any change imposed upon it. Simply, if you do something to a system that affects its equilibrium, the system will do the opposite in order to restore its comfortable state. For example, if you raise the temperature, the system is going to try to lower the temperature. The equation is as follows. Kp is equal to the partial pressure of nitrous oxide squared divided by the partial pressure of dinitrogen tetroxide. The graph that they're looking for looks a bit like this, and the next question wants you to explain why it looks like that. Initially, the vial contains only dinitrogen tetroxide, and the concentration of the nitrous oxide is 0 molar. As the dinitrogen tetroxide gets converted to nitrous oxide, the concentration of nitrous oxide increases to a certain point and then it plateaus. When the equilibrium is met, the concentration of the reactants and the products remain constant, but not necessarily the same. The concentration of dinitrogen tetroxide decreases until the equilibrium is met, and that part of the graph plateaus as well. If the sealed tube is cooled to 0 degrees Celsius, a color change from brown to colorless will be observed. Since the forward reaction has a positive enthalpy value, this indicates that the forward reaction is in fact endothermic and thus favors cooler temperatures. If the temperature is lowered, the system will try to restore equilibrium by raising its temperature. This will favor the backward reaction, thus increase the yield of dinitrogen tetroxide, a colorless gas. A strong acid will donate all of its H+ ions. For example, hydrochloric acid will dissociate to give you H+ ions and Cl- ions, while a strong base completely dissociates in water to yield a high concentration of hydroxide ions. Those are your OH ions, by the way. For example, sodium hydroxide. That will dissociate to give you sodium ions and of course OH- ions. The equation is as follows. Ethanoic acid, which is CH3COOH, will dissociate to give you the ethanoate ion, which is CH3COO- and H+ ions. When reactions occur, the reactants are used to make new products. Therefore, the concentration of the reactants will decrease by some amount, which we'll call X, and the concentration of the products will increase by some amount, which we'll also call. So for the change, ethanoic acid will decrease by X amount, H+ ion concentration and the ethanoate ion concentration both will increase by X amount. So at equilibrium, you'll have the initial concentration of ethanoate ions minus X, while for the H+ and ethanoate ions, you'll have the initial concentration plus X. So for ethanoic acid, we started out with a concentration of 0.30. So at equilibrium, we'll have 0.30 minus X. And for the products, of course, we started out with 0. So they'll be both 0 plus X, which is just X. Kc is usually given by finding the product of the products divided by the product of the reactants. So in this case, Kc is equal to the concentration of the ethanoate ions multiplied by the concentration of H+ ions divided by the concentration of ethanoic acid. The ethanoate ion and the hydrogen ion is equimolar, meaning they have the same concentration. And this is because they're in a 1-to-1 ratio. So if the concentration of the H+ ion is X, then it's safe to say that Kc is equal to X squared divided by 0.30 minus X. If X is equal to 0.0023 molars, then the concentration of the H+ ions is 0.0023 molars. Therefore, pH is simply equal to minus log to the base 10 of the H+ ion concentration. If you substitute 0.020023 into the equation where you have H+ ion concentration, plug that into your calculators, you should get 2.64. First, let's take a look at the arrow. The arrow is pointing from B to C. This is indicating the flow of electrons. It is very important that we know the direction of flow of electrons because that will help us identify which one is our anode and which one is our cathode. Electrons always flow from anode. to cathode. It's kind of like saying your ABCs without B. So B would be your anode and C would be your cathode. You so smart. Good. During the electrolysis process in a voltaic or even galvanic cells, it's used interchangeably. The following is generally observed. At the anode size usually decreases or its thickness decreases given that the electrode is not inert. This is because the metal electrode is oxidized. It provides electrons to the circuit and provides a solution of the half cell with metal ions. At the cathode, however, the cathode usually increases in size or thickness because the metal cations are reduced and deposits on the surface of the electrode. And again, this is only true given that the electrode is not inert. Reddish brown colored copper metal is deposited at the cathode. Potassium nitrate or potassium chloride, but are they always used in the salt bridge though? Although other salts may be used, they are the salts most frequently chosen because of their high solubility and ability to provide mobile ions. Alright? Now completing this table, so you have sodium oxide, which is Na2O, and oxidation state of sodium is +1. Magnesium oxide, which is MgO, +2 oxidation state. Aluminum oxide, which is Al2O3, +3 oxidation state. Silicon dioxide, SiO2, +4 oxidation state. P4O10, +5 oxidation state. And lastly, SO3, sulfur trioxide, +6 oxidation state. I hope you realize we're counting 1, 2, 3, 4, 5, 6. This is going to help us to answer the next question. So as you notice, these are period 3 elements, right? As you move across the period, the acidic nature of the oxides will increase. This can be further proven by the oxidation numbers. As the oxidation state of a central atom becomes larger, the acidity of the molecule increases. Just keep that in your little book somewhere. Well, keep it in your head because what are you going to do with it in your book? The following is a balanced chemical equation. So P4O10 solid is going to react with 6 water molecules in its liquid state, of course, to form 4H3PO4 aqueous. All the electrode potentials are given in terms of reduction. This is a fact, always true. If you check it, even in your data booklets, it's always given in terms of reduction. The smaller the electrode potential value, the stronger the reducing agent. The larger the electrode potential value, the stronger the oxidizing agent. Now, halogens are oxidizing agents. Therefore, from the table, you're looking for the largest electrode potential, that is the largest number. Since the chlorine molecule plus, 2 electrons giving you 2 chloride ions, that equation has the highest electrode potential. So it has the greatest tendency of the 3 halogens provided in the table to gain electrons and therefore would be the strongest oxidizing agent. Now we need to determine which equation of sulfur to use. You're going to choose the equation with the smaller electrode potential. This indicates the strongest reducing power, as I had said earlier, and coupling the strongest reducing agent with the strongest oxidizing agent will bring about the greatest change. So S4O6 2- plus 2E-, which is 2 electrons, will give you 2S2O3 2-. This equation should be written in the reverse because the electrode potentials, as I had said earlier, are generally written in terms of reduction, but S2O3 2- will be oxidized by the halogen. So the overall reaction should look something like this. 2S2O3 2- plus a chlorine molecule will give you 2 chloride ions and of course S4O6 2-. This is iodine. I have nothing else to say. Iodine. In reaction 1, chlorine displaces halogen Z, that is iodine, forming a brown I2 solution, and sodium chloride. In reaction 2, that represents a double displacement reaction. Silver will displace sodium and form AgI, which is silver iodide, which is the yellow precipitate seen, and of course aqueous sodium nitrate, NaNO3. Alright, so that was the completed paper, y'all. If you enjoyed this video, remember to leave a like. Also, leave a comment if you can. And go follow me on my socials at _TAM_EO. My name is Cameo-Lee, by the way. Hey! And also at young_genius.official. And check out my website at younggeniusofficial.com. Until next time, bye guys!